response on the anodic side. And there's a little bit of curve in the response related to changes in the what's happening in the cell in terms of polarization, but you then get a linear response which is related to the particular reaction that's going on in the cell. So this may be the linear slope for oxygen reduction or hydrogen reduction as a cathode process, and this could be the linear slope, and it will be a different slope for oxidation of iron to iron 2+ or aluminium to aluminium 3+ or whatever. And there's a handout on the corner there if you just grab one. So the linear response without the presence of activation is, without the presence of polarization, is what you get thermodynamically from what they call an Evans diagram. So we said we get things happening in the cell that cause polarization. And the first thing is activation polarization, so this is what we mentioned last time. And that's related to exceeding the energy required for the electron exchange at the interface. So remember, all these processes are surface processes between the solution and the solid steel. So we're interested in what's going on at this interface between the solid and the liquid. And to get electron exchange, we have to exceed an activation energy for that. And that's all activation polarization is. You have to nudge the potential a little bit higher than you're anticipating in order to kickstart the reaction. Otherwise, the process is extremely fast. So this type of polarization is not about the process being slow, it's just about it requiring you to exceed an activation energy. And you'll get the linear response that you get on an Evans diagram. We'll have a look at one in a minute on your handout. No, I'll come back to that. We then said there were some other polarizations that occurred in the cell. One related to the reactants diffusing through the solution to the surface to react, and the products diffusing away from the surface once they've reacted. And you get a concentration gradient through the solution. So there's concentration polarization, and that slows the process down, the reaction down. You cannot just draw more and more current from the electrode or from the steel surface or from the sacrificial anode in a real situation. There is a current limit. The other thing that happens is that the cell changes in its characteristics in terms of its resistance. So you get the possibility of an oxide film build-up on the surface, perhaps, making a layer on the surface. So you've got film resistance, and the solution itself will change in resistance as ions are used up from the solution to produce metal salts and precipitates. So the solution itself changes in conductivity, and you get resistance polarization as a result. So there are two reasons why you get, these are the two reasons why you get polarization curves instead of just seeing linear Evans diagrams. Okay, so that's more or less where we were. Oh yes, and we said everything starts off by obeying Ohm's law, I equals V over R, or in our case, E, because we're talking about potentials, and that E value relates to delta G, the reaction equation, because delta G equals minus NFE. So whatever reaction's going on, its Gibbs free energy is related to the potential that you see. And this is the basis of generating Evans diagrams, the thermodynamic information, without considering the impact of concentration polarization and resistance polarization. Okay. Yeah, so what we're going to do is look at the Evans diagram on your handout and look at this idea of mixed potentials. So what you've got on your handout is this diagram at the top. This is an Evans diagram. You can tell because the lines are all linear. It's not a curve. And what it shows is the theoretical response, the thermodynamic response of two electrodes. So what we've got is this electrode here, which is the hydrogen process, and there are two possibilities. There's a cathodic process, which is hydrogen reduction, okay, the blue line on there, and there, alternatively, if you apply a potential that's above the equilibrium value for hydrogen, you could get hydrogen oxidation as an anodic process. So that is one equilibrium potential or open circuit potential, and the possibility of going cathodic from it, or going, good morning, or going anodic from it. There's a handout on the corner. There is also down the bottom here another what they call half cell. And this half cell is for a metal oxidation. So that's the equilibrium value. Okay. And then there's a possibility of the metal being oxidized, which is the red line here, or reduced, which is the black line that's going off the bottom of the chart, but would actually run off down that way. Okay. So again, you've got an equilibrium value plus the option of oxidation or reduction from that equilibrium point. That data is available. It's thermodynamic data. It's related to the delta G value and to the Tafel slope for the particular reaction. What the Evans diagram allows you to do is to find a new potential, a new what they call mixed potential, which is for a combination of, in this case, this metal reaction and that hydrogen reduction reaction. And the new mixed potential is this one here. So, given some thermodynamic data, you can work out new values for different combinations of electrodes, or different combinations of reactions occurring, anode and cathode if you prefer. The intercept between these two lines is the new free corrosion potential for the new cell. I've got one other thing just sketched on here, and that is just to say these are Evans diagrams. They don't include any polarization data, but it is unlikely that the current will simply just carry on increasing linearly. In a real situation, that current eventually is going to curve off, and that's what that blue dashed line is to indicate that there's going to be some concentration polarization in a real system. And that in fact turns up in quite a lot of diagrams. So here's another one. Just see if I can make that better. So this is a very similar diagram. The same thing really, essentially. This one is, the difference is that this process is the oxygen equilibrium. So there's oxygen oxidation, oxygen reduction, which is our well-known cathode process. And that does experience concentration polarization. The current does get limited because the oxygen's got to diffuse through the solution to the cathode. Metal reaction, that's its free corrosion potential there. This is oxidation of the metal on this line, reduction of the metal on that line. And so the intercept of the anode process and the cathode process is here and gives us our new mixed potential for the cell between this metal and oxygen. It's the same concept as you've got on your handout. So, but the intercept is earlier on than it might have been predicted just from an Evans diagram, which would just carry on linearly plotting. So your activation polarization gives you your linear sections, concentration and resistance polarization gives you your curved sections. So if you want to find out how your pipe steel behaves in a particular environment, then you get to start off by creating a known surface area electrode of your steel. You're going to look at its potential current response, so you're going to want to measure the potential on that bit of steel, and that means using a reference electrode and, if possible, pointing that reference electrode so that it's porous frit is pointing towards the surface that you're examining. So we've got a reference electrode. And then you're going to need to power the system. You're going to want to drive it away from equilibrium. And so you need what they call a counter electrode. And quite often that is something that doesn't contaminate the system. So quite often that's a platinum sheet. So it doesn't corrode away or get attacked. So you've got a reference electrode. You've got a platinum, what they call counter electrode, and you've got your piece of steel, which is called a working electrode. So this is, put breath on there, but what I should really put is RE. And that's what they mean by 3 electrode cell. Yeah? So this is platinum counter electrode. Yes?
For the reference electrode, they use a hydrogen electrode or a different pattern?
For convenience, you'd probably use something like a saturated calomel electrode or a copper sulfate, or one of those ones that's in the plastic tube that's handy to stick into a cell. And of course, there's an output here. So you've got what they call a 3 electrode cell system. You've got the material you're interested in, you monitor the potential on that material, and you use another electrode, an inert electrode, to drive the current through your, sorry, got to be a bit careful there, haven't I? Depends whether it's whether you're galvanostatic or it's still current. It's still a high flow. It is current, but not to drive it. Okay, to allow current flow through your working electrode. And so what you use is a thing. Essentially a power supply across the counter working electrode. So we've got a mains controlled output going to the between the working electrode and counter electrode, a power supply unit. And that has a feedback loop. It takes the signal from the reference electrode and senses what the potential is on the working electrode, and it adjusts the flow of current until the voltage on the reference electrode is the one that was dialed up on the power supply unit. And historically, you used to do these measurements in a stepwise situation. So you dial a voltage onto your power supply, it would drive the working electrode to that potential, and then you would measure the current flow between the counter electrode and the working electrode. And you just keep adjusting the voltage, measure the current, adjust the voltage, measure the current. Now it's all computer controlled, and it will scan the range of voltage you want at a particular scan rate, usually in millivolts per second, and the computer just logs all the data for you. It's a way of getting accelerated data about how your steel behaves in an environment across a range of potentials. You've got to be a little bit careful about how much you accelerate the data, because the faster you sweep the voltage range, the further away from equilibrium you are. And so you'll see shortly that there is a technique for looking at how materials behave at different sweep rates. So we sweep the voltage, measure the current, and that gives us our EI curve. Okay, I think that's this one, hopefully. Yeah, okay, yeah. This one we'll do next. This is on your handout. Here are some polarization curves. I know they're for a real system because they're curves rather than straight lines. And what we've got here is actually 3 curves for the same steel, and it was some experiments done to look at a corrosion inhibitor. So there are 3 plots. The first plot is the performance of the steel in 5% hydrochloric acid, so in a slightly mildly acidic environment. And the current that you get is reasonably high. In milliamps per square centimetre. On the handout, for some reason, they've got milliamps slash centimetre per. They've done it twice. Okay. These sort of mistakes happen. The potential values here against the standard calomel electrode. The second plot is similar to the first, but has occurred at lower currents. It's shifted across a little bit. And that is the same solution, but with a corrosion inhibitor added to it. So you're getting lower corrosion currents in the second plot. The third plot is for what was brand new then, a new corrosion inhibitor, which is a benzaldehyde thiocarbazone, which I'm sure you didn't really want to know, but I like to keep trying that as a tongue twister. And what the graphs are illustrating is that the new inhibitor actually gives you even lower current densities than the old inhibitor. Why am I showing you this? I'm showing you this because this is one of the applications of the technique. It allows you to quite quickly, you could do this test in the lab in an afternoon, and you'd be able to demonstrate irrefutably that your product was a better inhibitor and was going to make your structure last longer than the old product. And you could even use the value you get. This intercept here is a current density called the exchange current density. There'll be another one here for the old inhibitor, another one here for the new inhibitor. You'd be able to take that current density and make a life estimate from that current density for your component. So it's a quick way of getting data. Okay. And the sort of things that you can determine are the corrosion potential, the corrosion rate, by which I mean corrosion current, And then what other things are happening, and we'll look at passivation and pitting in a minute. And also we can get, providing there's not too much polarization going on, we can get taffel slope data which relates to the reactions that are occurring. If you ever get any polarization data to look at, you need to check what the sweep rate was, because sometimes people get a bit too impatient and they sweep the thing too fast. So you need to know the sweep rate. And you also need to know the potential range of the sweep and where the sweep was started from. Those all impact on the result that you get. So it's very easy to get rubbish from polarization curve measurements if you apply the wrong sweep rate or sweep from the wrong part of the curve. And basically, what you should do ideally, if you've got if you want to do a plot, it's better to start from the cathodic end, go through the free corrosion, and then come out through the anodic. So you should sweep from negative to positive, ideally. And the reason for that is, if you swept the other way, this is where you're going to get all your corrosion. So your electrode starts changing surface condition, the electrolyte starts changing, the whole thing starts moving, and by the time you've started to do the cathodic curve, you're not dealing with a smooth polished surface of whatever, it's a pitted, corroded chunk of something. So it's better to start on the cathodic side, work your way around to the anodic side. But people make mistakes. So it is an accelerated test method, but you've got to use it properly. Okay. Well, that's the inhibitor testing, we've done that. All right, yeah. So one of the things that you can use the polarization curve for is for identifying passivation in alloys, and stainless steels show this particularly nicely, and they also go through the passive state and then start to pit, so you can get pitting potential values. So in the active region, we're just actively corroding. Passive, we've got a protective film, and for these stainless steels, that's a chromium oxide film. And then, as you continue anodically, you get past the passive range, and you begin to get pitting of the material. This isn't on your handout, but I'm sure you can quite quickly sketch this. What I've done is I've put an arrow on just to indicate the scan. So the scan has gone from the cathodic through to the free corrosion, starts to corrode, then passivates, at which you get very little current, despite the change in potential, and then eventually you get a pitting potential somewhere there. The scan is that way. This is your e-core. So, and this shape of curve is typical for a stainless steel. You know, you'd sketch that. Okay, I've got no numbers on there, no scale, but you sketch the general shape of it for any stainless. So don't worry about the bit of blurb here. Maybe I can block that out. There you go, it's gone. So this is our cathodic part of the curve. Then we get to our free corrosion potential. Then as we move anodically, the material begins to corrode, so that's the active part of the curve. And for a low alloy steel, the current would probably continue to increase up here. But this material passivates, so the current falls off, so we're getting passivation through A to B. The passive film is a few tens of nanometers thick, but it's enough to stop any significant current flow, so the currents are quite low during this passive part of the curve. And eventually the potential gets high enough to electrically break down the passive film, and you start to get pits forming on the material, and the pits start growing, so the current starts increasing again, and the potential at which that happens is called the pitting potential for the stainless. So again, it's a quick way of finding out what's happening to your material. Does it passivate? What's the pitting potential? You know, if you're operating your plant in this potential region here, then everything's fine, no problem. Run forever. As soon as it gets past the pitting potential, you're in trouble. Of course, there are lots of
How to measure this range?
in the 3 electrode cell. yeah, that we were just talking about with the power supply unit.
Okay, we'll measure by power supply.
Yeah. The only condition, of course, is that you measure this in a particular environment, a particular temperature and a particular concentration of the environment. And if the environment changes, if the pH changes, for example, then the potential at which you get pitting will change. The curve will shift with pH because that affects potential. So the data is a useful indicator of what is likely to happen, but it depends on how controlled your environment is. The other thing you can do is predict when you're going to get stress corrosion cracking. So by taking polarization curves at fast and slow sweep rates, you can predict the risk of cracking. And this is a classic method for trying to predict whether a particular environment and alloy combination may be susceptible to stress corrosion cracking. It was developed in the 70s and 80s by a guy called Redford Parkins, who has published an enormous quantity of literature on pipeline steel cracking over the years. He was involved with the intergranular and then transgranular failures on the Trans-Canada pipeline and so on. He's not terribly easy to read, but if you're looking for good quality references, he definitely published some very good stuff. So he developed this technique, and he also developed the slow strain rate technique that's used to perform stress corrosion cracking tests on materials. And this technique allowed him to make some predictions for the likelihood of cracking prior to having to do the actual mechanical tests. Okay. That's all right. So what you've got in your handout is this plot, and this is another polarization curve. Essentially all that's happened is it's been put on its side. So if I flip it temporarily, that way. Let's just get it right. What we've got then is what you're used to, which is potential at that side and current along the bottom. Where's my pen gone? Current along the bottom. But it's been put on its side. But it's the same thing. It's two polarization curves. And it was put on its side because we wanted to emphasize the change in current density. So you've got the cathodic part of the curve going down to the free corrosion potential, then the anodic part of the curve, and the material starts to actively corrode. But then, depending on the sweep rate, two things happen. If you sweep slowly, this is 20 millivolts per minute, then the material starts to passivate. If you sweep quickly, the material appears to continue to corrode. What's happening here is a question of time to get to equilibrium. What the slope curve's doing is telling you that if the material is held at these sort of potentials, then it will passivate. It builds up a protective layer and the current becomes quite low. If you sweep quickly through the region, the material is still active, it's still corroding. And that's essentially the condition that you want for stress corrosion cracking. What you want is we put a crack in here, or a defect. We want the surface to passivate, and the part of the sidewalls to passivate. But if fresh material is created at the crack tip because of the tensile loading, we want the material underneath to corrode. Yeah. So what this is saying is, yeah, it passivates if it's exposed to the solution for long enough, but if it's freshly exposed, it corrodes. And so that was the indicator that you could get stress corrosion cracking in this material, that there was a large potential difference, current magnitude difference between a slow scan and a fast scan in the same environment. So the material does passivate, that's the slow scan data, but if you expose fresh material, it will corrode, that's the fast scan data. Yeah.
Why would you have preference for the corrosion? Why would you have preference for corrosion at the root of the crack?
Because that's where the stress is highest. Yeah. That's where, most likely, where the oxide film will be broken down. Yeah. At the stress concentration. Just remember, there's some tensile stress here, whether it's residual or applied, at right angles to the crack growth. Okay. That's all I was going to say about the polarization curves. I just wanted to say one other thing in relation to polarization, and that relates to cathodic protection systems and looking at pipe potentials. And so there is a what they call an IR drop in cells, which means that the actual potential on the component compared to the apparent potential on the component is slightly different. And that's because of the polarization effects in the cell. And the way to check what's happening is to instantaneously switch off the current. You'll get a drop in the potential, an instantaneous drop, and then a more gradual drop off. And it's the instantaneous drop which is related to this IR effect, essentially the resistance in the soil. And you can then get your true pipe potential. And we'll have a look at that again next time. Okay, thank you. All right. Yeah.
Can I regarding your explanation about transform cracking? So, as I understand from your explanation, because of the passivate film, something like that. So when
So the surface all passivates,
yeah.
but if a stress causes that film to crack, you'll get corrosion. And then it'll passivate again. Because the film is brittle. So every time there's a bit of load applied to it, it cracks. Then you get corrosion, then it passivates. So it's a stepwise process.
Okay.
Yeah.
The initial condition we have a passivate film all the surface, including the
Yeah.
crack tip, but
Yeah. Well, you might not even have a cracked tip. It might be a flat. Well, there has to be some sort of stress concentration. Maybe it's a change in geometry. Yeah. But wherever that stress concentration is, that can cause the film to crack, and then corrosion will occur, and then it'll passivate again. So you've got to have a combination between tensile stress and passivation, film formation.
Okay, thank you.
Oxide film rupture mechanism.
So the root cause is the film, the loss of film because of
The
Stress
film
concentration.
mechanically is
Yeah.
brittle,
Yeah.
whereas the metal underneath is ductile. So it will open up if there is a load applied to it, and then the bare metal underneath is exposed to corrosion again.
Okay, thank you.
You're welcome.
Dr. Charles, I've been working on my literature review,
Good.
and these are the topics I plan to discuss in the literature review. So I'd like to. Could you please tell me what do you think about it?
Okay. Yeah.
Any suggestion or comment?
It just looks like this is quite a small component in comparison to the rest.
Yeah.
Maybe there needs to be a bit more here.
Okay.
Because there must be more than one program.
Yeah.
So,
Exactly.
development of the...
Yeah, like lamps is another very popular. Lamps.
Yeah, right, yeah. But,
Okay.
development of modelling of hydrogen diffusion or something like
So
that.
I would
Should
say
be a-
instead of general lattice utility program, I would say molecular dynamics program.
I just think there should be more sections about computing,
Okay.
because you've
Yeah.
talked very much about the
Yeah.
steel and the hydrogen, and then just thrown this in the end.
Yeah.
This is probably
It's a
development
host.
of models,
Okay.
then the program that you're going to use.
Okay.
You know, so it's got a little bit more, a little bit bigger.
Yeah. Yeah. Thank you.
And,
Yeah.
and are you going to do? Are you going to do much about steel microstructure? We can't model that, can we? We need a little bit about ferrite,
Yeah.
perlite banding and things, but.
So should take it off? Probably.
Depends whether you run out of space, because I was told your survey can't be very big. I'm told.
Yeah.
It's
So
a shame.
my priority should be this part from down, right? Like,
Yeah,
if I have
you're gonna
space,
have to try it for size.
Okay,
Yeah.
okay,
yeah.
yeah. Okay. Thank you so much.
That's good then.
Yeah.
Yeah. Cheers.